Despite proof of otherwise and the content I'm about to show you, I'm not mad.
At least Mummy says I'm not. Mummy's never wrong.
As proof of my lucidity, some extra content will be released on YouTube. Mostly explaining why I'm wearing a tie over a t-shirt. It will otherwise in no means affect the content of this video. So much to see, so little time. I'm obviously no specialist. And yet, I'm going to try and startle you the same way I was personally mind-blown by the wonderful world of quantum physics. We might as well start from the beginning. You see, from 1908 to 1913, Hans Geiger and Ernest Marsden, under the supervision of their professor Rutherford, started realizing a couple of experiments that, well, literally shook the scientific world. These were known mostly as Rutherford's gold foil experiment, and with it, Rutherford proved that his own professor Thomson's atomic theory was incomplete, and installed his own. But is that a problem? Oh, indeed there is. You see, Rutherford's model had essential inconsistency that according to classical mechanics was, well, it made it simply impossible to be. The negative parts of an atom would collapse into its nucleus, and hence, we wouldn't be here. And, well, as far as I'm concerned, I'm here. Luckily for Rutherford, however, even though his model didn't quite be the most complete and accepted one today, it did get some sustention that came from, well, you guessed it,
Quantum physics!
According to Rutherford's observations, the electron, which is the negatively charged part of an atom, would simply spiral around, losing energy and shooting electromagnetic waves all over the place until it hit the nucleus and stop existing. And now I finally get to the first of the 4 fundaments I want to present in this video, and that would be discrete energy levels. Dun dun dun! Yeah, my sound effects, they're not really that good. Anyways, your face right now is probably like this. But don't worry, I'll explain. Basically what it means is that electrons can't go frolicking wherever they want anymore. Well, they can actually still frolic quite a lot, but I'll get to that. You see, now they are bound to layers, or shells. But what does a shell mean? Well, you can think about it like an actual nutshell, with the nut being the nucleum and the shell being, well, the shell. The thing is that there are more than one shell, each one containing each other, so it's easy to think about it as layers on an onion. Bound to means that the electron is on that shell, not inside it, on it. These shells are basically energy levels, since the more energy you feed to an atom, the further away the electron will move from the nucleus, and vice versa. And discrete is the contrary of continuous. What that means is that your first shell is going to be your unit. We call it a quantum in this case, and all subsequent shells that go around it are just multiples of this specific shell. What does that mean? You will never find an electron in between shells. There is no half shell. Either you have a shell, or 2 shell, or 3 shell, but you see, it's always a multiple of your first shell. Since electrons can't go in between shells, the electrons literally teleport themselves from one shell to another. Yeah, how's that Mother Nature for you? How does this help Rutherford? You see, once the electron is bound to a shell, it can never go below the minimum layer, hence it will never actually reach its nucleum. World saved. But now I must move on, and to break this boring monologue, let's go to a thinking exercise. The name of this exercise is Scrooge's cat. In our demonstration, we're going to be using Fluffy to represent our live cat, and Patty to represent our dead cat. Poor Patty. The experiment itself is quite simple. We will be putting a bomb and our live cat into a box and closing it up. Now it gets interesting. An hour from now, I'm going to open the box again, and there will be a 50-50 chance of finding either a live cat or a dead cat. Here's the catch. I don't know what's inside the box. I don't know if he's alive or if he's dead. And yet, maybe, just maybe, he's neither. He may as well be alive and dead at the same time. You see, on a point of view, that seems kind of, well, outrageous. I mean, how can something be alive and dead at the same time? Zombies? Yeah, in classical mechanics, that really is very weird. Yet, quantum physics seems to only agree with this. It's called superpositioning of states. Keep that in mind. Together with our second fundament, it will clear our third. Our second fundament can be proved by a very interesting experiment called the double fend experiment. Picture this. You're at a bowling alley, just throwing your bowling balls. At the end, we're going to put a detector so that every time the bowling ball passes by that detector, we know where it was and how it passed. The exact position. Now, right down the middle, we're going to put a plate that's going to stop the bowling balls from passing. And on this plate, we're going to put two slots in it, two fins. And now the bowling ball can only pass through these fins. Except we're not throwing bowling balls anymore. We're throwing electrons. We're throwing particles. And you know what happens? Well, we expect at the detector to only be two slots, behind the fins where the particles are passing by. And yet the result was remarkable. Right down the end, we didn't have two distinct stripes, we had several. And there were even cases of electrons in between them. And here's our problem. Picture our bowling ball again. How can it pass by the detector right in the middle where it was blocked? It could only go out through the fins and not through the middle of it. There's only one possible explanation. Particles also behave as waves. I suppose I should give some clearing on what a wave actually is. You see, while a particle is something that can be pinpointed in space, a wave is different. It's more of interference that just moves throughout space. You can quite literally see it as an ocean wave. The movement, it's not something you can pinpoint in one exact spot, yet you know it's there. It's moving through space. But wait, you're mad. I'm not a wave. I'm a particle, see? I can be pinpointed. I'm not bugging out all over the place. That's where you're wrong. Well, not entirely, since the puzzles are not really bugging out all over the place. But you see, our wavelength is so small, it just can't be detected on a daily scale. Yeah, remember superposition? Now that we understand that particles have a wave-like behavior, we can finally get to the third fundament. Despite its importance, we're going to move through this fundament quite quickly, since the next one is my personal passion. Anyways, remember when I said that electrons could still frolic quite a bit? That's because they can't be pinpointed. The moment you analyze them, they're there, in that exact spot, acting like a normal particle would be. But the moment you're not looking, and here's where things get spooky, it's not there. It's actually everywhere. It's not that you don't know where it is. No, it literally is everywhere. This really bugged out Einstein since he said, no, this isn't possible. There must be a variable that we don't know. It's not because we're looking at it that it's going to change. No, it can't be this way. Yet he eventually was proven to be wrong. And this leads us to my final topic, and that's going to be entanglement. You see, Einstein being wrong about it is by no means bad. Actually, without the EPR paper published in 1935 by Einstein, Podolsky, and Rosen, well, actually it was more of a philosophical note than actual mathematics and physics. Anyways, without that saying that quantum physics is simply incomplete, we would probably never have gone so far. Einstein called entanglement spooky action at a distance, since it quite frankly just hit relativity right in the face. Entanglement essentially says that particles can communicate with each other on opposing sides of the universe. Instantly! That means that they can send information faster than the speed of light itself. You see, when we analyze a specific characteristic trait from one of these particles, we immediately know a similar characteristic trait from the particle on the other side of the universe. The first time I read about this, the first thing I thought was, yay, teleportation! Unfortunately, Mother Nature crushed my dreams. You see, there's a 50-50 chance you find a determined characteristic on one particle. And you can't actually do anything about it. You can't determine what you're going to find. You'll only know once you've looked at it, and once you've looked at it, it's defined. Hence, the other one on the other side of the universe is also going to be defined. Yet, you can't do anything about it. You can't even send information through it, since you can't control what you're going to find on the first one. I continue to read about it, and you see, it gets even weirder. The moment you determine one of its traits, let's say color, it's always going to have that color if you measure it again. See, I'm going to measure color. It's the same color again. But if you measure something else, like, let's say, hardness, is it hard, is it soft? Then once you measure color again, it might not be the same color. It might have changed. Just the act of measuring might influence on the result. And then I thought, aha, we can use Morse codes to communicate with each other. And then Mother Nature crushed my dreams again. You see, once you measure it from here, you break the connection. It's a one-way trip. You only get to figure out what you're going to have on the other side once. Once you've measured it, if you change measurement, you break the connection, and hence, you can't do Morse. If you think quantum physics only affects the very small and has nothing to do with your life, that's where you're wrong again, my friend. Without quantum physics, the microchips that compose your electronics, yes, the one you're using to watch on your computer this video right now, they simply wouldn't exist. I by no means want to teach quantum physics in 10 minutes. That's insane. But what I do want to do is to entice you into diving and delving deeper into this wonderful realm of physics. And maybe, but just maybe, show you that maybe the future isn't up there. It's just a grasp of hand away.